I'm sorry that I cannot be at the meeting, so I'll have to give this presentation in a Zoom link. And as you can see, what I'm going to talk about is how people found out which elements the stars are made up of, or more generally, the material composition of the universe. But I'll keep to the pre-World War II period. And before I come to that, I think it will be useful to take just a brief look at the modern knowledge, which we have here in the chart. So this slide gives the material composition of the universe. I'll come back to that. But what we know is that the two lightest elements, hydrogen and helium, makes up almost all the matter of ordinary matter in the universe. And I'll also, so helium and hydrogen is about 98%. All the other chemical elements in the periodic table are somewhat strangely called metals in the terminology of astrophysicists. So oxygen and neon and what have you, phosphorus, they are metals according to their terminology. There's another point I need to emphasize, that this chart, which we have here, is relating to so-called ordinary matter, as we found in the stars. And according to modern knowledge, this is only about 5% of the total mass energy of the universe. It's well known that dark matter makes up much more than the visible matter, about 28% or something like that. And that dark energy, which also a kind of matter, makes up nearly 70%. But obviously, these things were not known in the period that I'm going to talk about. Spectroscopy, of course, was the method which enabled scientists to get some knowledge of the matter in the stars. And in the late 19th century, it was far from obvious that there could not exist elements in the stars which are not found on the Earth. And that was indeed what several very well-known scientists came up with. There might, it was what was it proposed, exist a solar element, and the reason for Charles Young, an American astrophysicist, to make that proposal was solely that he couldn't identify certain spectral lines found in the coronal part of the sun. So he and other people hypothesized the existence of an element called coronium, which possibly only existed in the stars. People looked for it on Earth and they couldn't find it. Remarkably, they had various reasons to believe that the atomic weight of coronium was less than that of hydrogen, that it was a so-called subhydrogenic element. And it was not the only such element, because somewhat later, we have another non-existing element, which for a period of time was taken quite serious, called nebulium. That was based, again, the philosophy was the same. William Huggins in the late 19th century found some very distinct spectral lines from the faraway nebulae, and he couldn't identify them with any spectral lines from the laboratory. So he suggested, and other people suggested, that nebulium is a particular element of the nebulae. But of course, both coronium and nebulium are non-existing elements. That wasn't obvious at the time. These spectral lines on which they were solely based were eventually, but it took a long time, identified by means of a quantum spectroscopy as due to other elements, ionized hydrogen or ionized iron. So one might believe that, especially with regard to coronium, which has an interesting history, that there couldn't exist an element with atomic weight less than hydrogens. But that, I would like to emphasize, was not obvious at the time. By 1915 or thereabout, an element was defined by the nuclear charge of the atom, or the number of protons in the atom, we would say today. But that, of course, was not the definition at the time. At around 1900, the definition of an element was given by its atomic weight, and there was no particular reason why the atomic weight should not be less than 1. And indeed, the founder of the periodic system, the great Russian chemist Dmitry Ivanovich Mendeleev, in a late version of the periodic system, this is from about 1902, and you can see here in Russian his version of it, a very clear version, but there are some surprises, namely that you can see before hydrogen and before helium, we have two elements which Mendeleev called X and Y. He thought that Y might well be coronium, and the even lighter element X he identified with the ether. But all that soon changed, and by 1915 or thereabout, these elements were not taken seriously any longer. So the standard view at about in the early part of the 19th century was that the stars are essentially, but not wholly, of course, composed of the same elements as on Earth and roughly in the same proportions. So in other words, the stars were, from a chemical point of view, a kind of Earth, a kind of heavenly Earth. That is what the American expert in spectroscopy, Henry Rowland, pointed out in a paper 1891, as you can see from this quotation, that the Earth, if it was heated to the temperature of the sun, would be basically the same as the sun. And about 20 years later, this belief was confirmed by Henry Russell, the great astronomer and astrophysicist, who in 1914 explicitly refers to Rowland's opinion that that the stars do not differ very significantly from a chemical point of view from the Earth. And that indeed was the common assumption. It was just an assumption. There was no measurements which supported it, but this assumption was first questioned in the mid-1920s. And I have to say a few words. No, let me just mention Eddington as well, because he, of course, was perhaps the leading astrophysicist of the period. And as in the view of Eddington, hydrogen played a most important role in the stars. Eddington was not primarily interested in the element composition of the stars, but he was very interested in the question of stellar energy. And instead of ascribing stellar energy to a gravitational contraction, such as was the traditional view, in about 1920, he hypothesized that nuclear reaction might well be the source of the star's energy, and that from hydrogen atoms, or we would say protons, heavier elements might be built up. That is the same idea which he fleshed out in considerable detail in his later masterpiece, The Internal Constitution of the Stars, published in 1926 and republished several times. Again, his primary interest was to why the sun shines, and he he discussed two different hypotheses. One of them was the building up processes when four protons results in a helium-4 nucleus, and the other was a process which, from a modern point of view, is not possible at all, namely an annihilation process between protons and electrons, in which they simply disappear and they leave some high energy radiation. As to the second of the processes considered by Eddington, he said how the necessary materials of four mutually repelling protons and two electrons can be gathered together in one spot baffles imagination. And it does, of course, and I mention this quotation because all people at the time, thought that the atomic nucleus consisted of protons and electrons. As far as the abundance of hydrogen in the stars, he was satisfied with some 5 to 7%. This common assumption that hydrogen was not very abundant in the stars was first questioned in the very important dissertation by Cecilia Payne. Payne was British, of course, but at the time she had went to America, where he studied. She studied under Shapley, and she wrote she wrote her dissertation on stellar atmosphere, which was published by the Harvard Observatory. And in this dissertation, she presented evidence in form of spectroscopic data that hydrogen and helium was by far the most abundant of the elements. On the other hand, this view went against the traditional view, and in the end, she concluded that these ratios, the abundances, were improbably high and almost certainly not real, as she phrased it. So for a couple of years, the standard view was maintained. Payne's ideas were not, or her data were not generally accepted. But in the course of 4 or 5 years, that situation changed drastically. So let me go to the situation in the very early 1930s, where a number of people followed up on Payne, and their investigations showed that hydrogen is indeed by far the most dominant element in stellar atmospheres. Here we have Payne, and we have the Irish physicist William McCrea, and we have the German quantum physicist Albrecht Unsöld, and they all agreed that hydrogen is very abundant in the stars. Now, let me see. Yes, so hydrogen was realized to be the most abundant element. Helium was a somewhat different story. The data about the helium abundances were not very good, but in the late 1930s, the Danish astronomer Bengt Strömgren, who worked in the United States, he and other people came to the conclusion that there is a large amount of helium in the stars. Here I have presented the data from Strömgren in that period, and he calculated the abundance, the relative abundance, of course, of hydrogen and helium in the sun and also in the star Sirius A. His data are not very good, but they are still in rough agreement with later knowledge. As Strömgren noted later on, the reason why he took helium seriously was indebted to the German quantum physicist Carl Friedrich von Weizsäcker, who at the very same time had come up with a most interesting hypothesis, which I shall show you very shortly. And Weizsäcker and Strömgren were friends. They knew each other from Bohr's Institute in Copenhagen, where they both had studied. So let me say a few words about Weizsäcker and his work from that period. Weizsäcker was, first of all, a nuclear physicist. He was not an astronomer. But in 1938, he published in a German journal, the Physikalische Zeitschrift, a very interesting paper in which he not only tried to explain the stellar energy, but also tried to explain why, to explain the abundances of the chemical elements. And we have indeed in the Weizsäcker's perhaps not very well-known article, a kind of Big Bang theory. He had the idea of a Big Bang, as you can see from this quotation, but he had not the idea of combining the Big Bang with relativistic models of the universe, that is, with general relativity, which only came with Gamow later on. But Weizsäcker suggested various nuclear reactions which would result in elements more heavy than heliums. And in order to compare his calculations with those with empirical data, he relied on the data from a Norwegian geologist who's probably not well known among astronomers, but who should be, I believe. His name was Victor Goldschmidt, and he was a professor of geology and mineralogy at the University of Oslo in Norway, and a great expert in geochemistry, but also in astrochemistry. And in a paper from 1938, he outlined what at the time were the most reliable percentages of the elements, not only on Earth, not only in the stars, but in the universe as a whole. So let me show you his data. And here they are to the left. That is one version of Goldschmidt's 1938. And notice that it's a logarithmic graph. So the difference between the abundances are underestimated, so to speak. And also notice that Goldschmidt took into account not only the chemical elements, but also the various isotopes. Indeed, his graph from 1938 are in qualitative agreement with modern data. In the other picture, you can say you can see the same kind of a graph from a modern point of view, and they are in fair agreement. So that was very important, and it became even more important after World War II, because Goldschmidt's data played a crucial role also for Gamow, and later as a physicist and cosmologist. I would like to end my talk with a term invented in 1940, namely cosmochemistry. Cosmochemistry, I mean, is a new term, and it was actually coined by an astrophysicist, a German-American astrophysicist, very well known at the time. His name was Robert Wildt, and he wrote in 1940 in an Italian journal a title in which a paper in which he introduced the term cosmochemistry, arguing that cosmochemistry is a chemistry not only on Earth, but as valid throughout the universe. And after World War II, this highly interdisciplinary science called cosmochemistry flourished. It was interdisciplinary because it involved not only chemists and physicists and astronomers, but also geologists to a large extent. This journal, which was a key journal for that kind of science, Biochemica et Cosmochemica Acta, was founded in about 1950 and was one of the journals which Gamow and his allies read and was inspired by. So I think that this is about what I have to say. And I understand that other speakers will take up the question of element formation from a cosmological point of view in a later address. Thank you for your attention.